SPUD, an autonomous solar panel cleaning drone.
In the dry and sunny state of Arizona, solar panels are a growing market in the residential communities due to their potential to save people thousands of dollars in energy costs. Over time, dust, dirt, and other foreign debris collect on the surface, limiting a solar panel's efficiency. Cleaning residential solar panels manually poses a safety risk as well as takes a significant amount of time. Industrial-sized drones that are engineered to do the same cost 5 figures and are not meant for residential scales and shapes. SPUD offers a solution that will allow the general population to have access to methods of cleaning their solar panels in a safe, time-effective way that also saves the providing company money. SPUD will be used by the sponsor's company as a service and not sold as a commercial product. At time of deployment, a technician from the company will take the drone system to the customer, ensuring they have extra batteries and a full tank of water. When the technician arrives at location, they will place the pressure washer on the ground next to the truck and the drone on the ground facing the building. As soon as the technician flips a switch on the remote controller, the drone will fly towards the building, completing a scan of the building bounds and roof to find the solar panels. As the software is processing data and finding the route for the drone to follow, the drone returns to the starting location to allow the technician to connect the water system. At this point, the technician flips a second switch that puts the drone into a cleaning state, in which the drone follows and cleans along the calculated path. Once the drone has completed its path, it will return to the starting location. The SPUD system can be broken down into 3 subsystems: the water system, the drone and thrust system, as well as the software and navigation system. The drone body and water system are connected through a fabricated nozzle holder, and the software provides glue and autonomy. Each subsystem played a vital role in the functionality of the product.
Hello, I'm Ethan Eshbasoa, and I am the lead for the water system component of the SPUD. Our water starts off in this 40-gallon tank, which is going to be elevated 3 feet above the pressure washer. With that height difference, it'll supply 4 gallons per minute through this hose to the pressure washer. The pressure washer has to receive at least 2 gallons per minute in order to function, and it takes that 2 gallons per minute and pressurizes it to about 1,150 psi. Once it's done that, it sends it through this long hose, which is 150 feet in length. As it travels through the hose, makes its way to the drone, it'll lose about 200 psi from friction losses. So by the time it makes it here, it'll be at around 900 psi, give or take. It will go through these components and come out here, the nozzle, to clean whatever is beneath it. These components have an operating pressure of at least 1,200 psi or higher. This whole contraption is attached to the bottom of the drone.
The technician first places the drone on the ground facing the building. After flipping a switch on the remote controller, the drone flies 50 feet in the air. The drone then flies towards the direction of the building until it notices a jump in the distance reading. The drone then follows around in an arc until it notices the jump back down. Using these 2 points, the software creates a trajectory for the drone to follow. The drone then follows the trajectory in a wave-like pattern until it gets an unexpected reading, following around in an arc until it reaches the expected reading. Using the previous trajectory and the new marker, a right angle and new trajectory is created for the drone to follow. This pattern continues until the drone reaches the starting marker. To optimize the efficiency of information gathered, the drone performs scans in diagonal parallel lines spaced approximately 5 feet apart, creating lines in 3D space. This allows the software to get a good enough reference to determine where the solar panels are. Once the solar panels are located, a series of points 3 feet apart are queued up in terms of next nearest point.
Hi there, my name is Carmen Timmer. I'm an electrical and computer engineer here at the U of A as an online student. My role in this project was the thrust system lead, which carried the water system and used the navigation system. I did most of the research to make sure that all these individual parts worked in tangent with each other and assembled it with my teammates in person. The challenging thing about this project was the different design changes that we had, and we had many of those. And I had to make sure that all the parts that were chosen worked well with each other and were in design spec for that particular spec. Like keeping in mind that this drone had to be small while making sure it had the strength to lift up everything and navigate smoothly was a delicate balance that I had to learn. What I'm most proud of with this project is me expanding my knowledge about larger drones. In the past, I've only worked on smaller drones about the size of my hand, called tiny whoops, and they were only for indoor use. So, expanding my knowledge with larger drones of this magnitude was nice. It was a lot of fun, but also very challenging, and definitely most proud of. What I want people to understand is that on design day, that this drone wasn't something that just to make a drone fly. We wanted to make sure that it was as autonomous as possible, that could work in small spaces like neighborhoods with limited spaces between houses to clean these solar panels. My efforts in this were keeping everything in balance between the electrical part with the aerospace part with the size of this drone. I learned so much about different engineering disciplines such as aerospace that I never had to consider in any of my class projects as an ECE major, such as how can I make my devices that I've put together electrically and I know that it works onto a flying system. But I'm glad I did this project as I've grown both as a person and a future engineer. I hope that future teams surpass us in making a better drone and that they grow as much as we did.
This project was significantly more complex than any of the team could have expected, which meant there were multiple changes made throughout the entire timeline that ultimately moved the goalpost. By the end, the team was able to create a working prototype that included a water system and a drone with autonomous software. While working in a multidisciplinary team can be difficult at times, it allowed us to create and document a system that would have been impossible for just one person to complete. SPUD has the potential to be improved in significant ways, given enough time and a large enough budget. More analysis can be done on soaps or other cleaning methods, as well as ways to improve battery capacity or increase thrust strength. A mechanism to allow the software to control the water flow would also increase the drone's overall autonomy. SPUD demonstrates the feasibility of maintaining solar panels in a safe and sustainable way. There will always be ways to improve a project like this, but the progress our team was able to make in such a short amount of time is a promising start to a better future.